we will talk about infinite dimensions briefly, just to set the stage for path integrals. And then, time permitting, we will discuss continuous time open system dynamics. I guess the particular Markovian dynamics. Okay. So the first thing I want to do is recap some elementary facts about infinite dimensions. So we gave our axioms that quantum states belong to a Hilbert space. And the problem with that was that our position and momentum operators, the eigenstates of them, don't belong to a Hilbert space. So here's the problem. So infinite dimensions. Are not elements of a Hilbert space. Okay, so recall we have our Hilbert space L2R, which is the space of square integrable functions. So that means we have f and g are elements of L2R. Tells us that the integral of f squared dx is less than infinity. And similarly for g, integral over x minus infinity to infinity. Which guarantees that the inner product fg is also less than infinity. However, the x operator has eigenstates. Essentially, it's x acting on delta x minus x naught is equal to x naught. So somehow the eigenstate of x is the Dirac delta function. And for p, we have the e to the I kx is equal to, let's see, we get ik comes down, so we get two i's. You get plus h bar k e to the I kx. So in other words, these are eigenstates because we get a scalar, but delta x minus x naught squared integrated is not well defined. I don't even know, I'm not sure how to evaluate that, in fact. But it's clear in the case of momentum. e to the I kx squared is going to be equal to 1, and this is equal to infinity, which is not less than infinity. Does anyone know how to evaluate this? Is that a meaningful?
Take a Fourier transform. It's the same as the other thing.
Oh, you get the same. You get infinity.
Yeah,
Okay.
Infinity.
All right, I'll believe you, but I'll still put a question mark. All right, so how do we rectify the situation? So there's an elegant solution to this by von Neumann, which I won't cover. We'll just look at Dirac's solution. So probably, well, I guess this is a bad salesmanship job. The best solution is due to von Neumann, and I won't tell you about it. Because the mathematical overhead is too involved to get into, given our small amount of time. Best solution due to von Neumann. I guess, basically here, that's Google it. I keep promising to give you guys some handout, which is my lecture notes on this. So it'll be in my lecture notes. You guys have to keep reminding Aggie to keep pestering me to get organized and send that file to her. Or see my notes, assuming I distribute them to you as I promised. And we're going to look at Dirac's solution, which is a bit of a stopgap solution. But it's the one that you all learned. All right, so you might as well know what's going on from what you've seen already. Dirac's solution is the usual. It's the usual approach, usual textbook approach. Okay, so Dirac's solution is to say, okay, let's allow our space of states to live in a bigger space than the Hilbert space. So basically introduce a triplet of spaces called a Gelfand triplet. So we have three spaces which are omega, h, and omega with an x at the top. So here h is our Hilbert space, and this is called the rigged Hilbert space formalism. I think I mentioned this already, but here the rigged is supposed to refer to an equipped sailboat and not a rigged casino. Although you can think of it either way because it is kind of a kludge. But this is called rigged Hilbert space. And so the idea is that we define omega called the nuclear space to be the subset of Hilbert space functions that converge very fast at infinity. I'm sorry? So we want phi is an element of omega if it satisfies this stronger condition that phi of x squared times 1 plus x to the polynomial power m dx is less than infinity for every m for every integer m. So as long as phi converges with this weighting factor, which of course makes it harder for it to converge because x is growing, then we say it's an element of the nuclear space. So the idea is that phi of x must go to 0 very rapidly. Okay, then we define the extended space which consists of all functions whose inner product with the elements of the nuclear space is finite. As this set of functions chi such that the inner product of chi and phi, I probably shouldn't use Dirac notation here, chi complex conjugate of x, phi of x, dx is finite for every phi in omega. So the important point, as you can verify, is that e to the ikx and delta x minus x naught are elements of the extended space. And then we have, and then as a consequence, we can have well-defined formula. For example, we can take, let x hat x equal x, x. Then the idea is that x is an element of omega x. And similarly, we have p, I guess we'll call it k, is equal to h bar k, k. And it turns out that we can define an inner product between x and k, which is the usual, which is what you normally want, which is, e to the I h bar k x over 2 pi h bar to the half. And more importantly is that then we can also write down a generalized spectral decomposition. And this is, of course, the really useful tool for evaluating expressions. We can also use a generalized spectral decomposition. Where you can write x as equal to the integral over dx from minus infinity to infinity of x. Sorry, my chi may not be distinguishable from my x. Is that what's happening? Yeah, so this is supposed to be a chi. So here's my calligraphic font here. All right, so hopefully that's so. An x has no little hook on it. Is allowed. So this is allowed because we're defining these objects to be elements of the nuclear space. And similarly, we can do a resolution of identity as just integral over dx x. And a resolution for P that's integral over dp pp. Here P equals h bar k. And then, of course, we recover wave mechanics. So then if you have some wave function psi, we can express it as a wave function, which is equal to x psi. Or strictly speaking, x is in the dual space of the extended space. So this is all now allowed. So the things you were doing before and talking about quantum mechanics as being a theory in a Hilbert space, well, it's not quite true. We can do these things that you learned to do in undergrad quantum mechanics as long as we understand that we have this greater structure. And anyways, this whole thing is unnecessary because of von Neumann's solution, but that's what's going on there. So von Neumann's solution allows us to just preserve the idea that Hilbert space is the fundamental space of our states, and there's just a more subtle way of handling the momentum and position operators. Von Neumann's approach? Yeah, it uses projector-valued measures. So the term PVM is a projector-valued measure. It comes from this idea of defining operator-valued measures and using that strategy to accommodate the kinds of things you want to use to describe position and momentum.
Do we know that for dimensional spaces, the dual space is isomorphic to the ket space?
It's probably not isomorphic to it, but this is something I'd have to check.
Not in general, but it's true for Hilbert spaces.
But it's not a Hilbert space.
Okay, yes. I mean, so the dual space of omega looks like omega x.
Yeah, maybe omega x and omega are dual to each other. I don't remember.
One of the usual ways to define it is by saying, to do this is by saying omega is short space and omega x is the dual space to short space.
Oh, okay.
Yes. What is short space?
Exactly.
It's this nuclear space.
Also imposing that the nth derivative vanishes like this.
Okay, so now that we've done that, we can now happily use these constructions and now discuss the path integral formulation. Okay, last year I motivated this via a classical Markov process, just as a process on a probability space. This year I won't do that. If you're interested in that, you can just look at the lecture from last year, which is on PERSA. Instead, I'll launch straight into the quantum mechanical version of it. So recall our time evolution is that we have psi of t is equal to u of t naught, psi of t naught. And then, of course, we can convert this into wave functions. We can convert to wave mechanics. Where we just we would take x psi of t defines psi of x of t. And then we have psi of x of t is equal to x u t naught psi of t naught. And then we insert a resolution of the identity in terms of these functions in the extended space. So here we have this expression here. Okay, but we're going to use the variable x prime. So then we have psi of x comma t is equal to x u of t naught, and then we insert dx prime, x prime, x prime, and this acts on psi at t naught. So then we have psi x of t is equal to a function g xt x prime t naught acting on psi of x at time t naught, where we've defined g of x t x prime t naught is equal to the transition amplitude of the unitary propagator. Now what we want to do is we want to divide the time interval into n steps of duration. Yeah? Did I forget it? Yes, thank you. In fact, yeah, there's no x prime dependence here, so I have to integrate over x prime. In fact, this is an x prime there. That's a typo. So here we integrate over dx prime. Thank you. So that means in terms of our unitary, we have t naught is equal to u of tn, u of tn minus 1, all the way down to u of t1 t naught. I think I'm dividing it to n plus 1 steps, but you guys can figure that out. Okay, so then the same thing happens with the propagator. This is a bit of a pain to write out in full. But we have gx of t x prime of t naught is then equal to a propagator associated with each of these time slices. So we have g of x of t relative to xn tn times g of xn tn, which is propagating from xn minus 1 tn minus 1, and so on until we get to the first step, which is x1 t1 x naught t naught. Yeah?
Like the composition of u as the product, so all of this, you require that you can be factorizable like this in time intervals?
It's an approximation, which we're going to claim is valid. I'm going to come to that. But yeah, we're going to assume that this is valid in the limit. We're then going to take a limit that delta t goes to 0 later.
But if you use like a one-parameter family of unitary transformations,
Yeah, sorry, yeah, that's right. U will be self-commuting if it's a one-parameter family, right? So if you have, e to the I ht, so we're assuming h has no intrinsic time dependence. So then e to the I ht is equal to e to the I h over 2t times e to the I h over 2t, because it commutes with itself. So now, in fact, now we're going to look at when this breaks down. So we're interested in some Hamiltonian h, which is equal to a kinetic term plus a potential term. So consider this situation where t and v do not commute. So each individual time step now, the system's evolving for some time delta t under this Hamiltonian. So here we've taken the full action of the Hamiltonian and expressed that we can do this is an allowed move, but the next step is not a legal move unless we make an approximation. Because what we want to do is we're going to write e to the I h t as e to the I tt times e to the I, let me call this delta t, e to the IV delta t, and here let's add the h bars for completeness. All right, so this is not allowed.
Just checking, you do want to integrate it all, but.
Oh, I forgot all my integrals. Oh, geez. Yeah, thanks. Here, maybe I can compress this. So here we want to add an integral over, this is a multi-dimensional integral. We have dxn dx1. Thanks for catching that. Then we have gxt x naught t naught, where you have to integrate over a resolution of the identity at each step. So it's basically this integral associated with this resolution of identity, but we've done it now at every time step. Okay, so returning to the actual approximation we're going to apply is we're going to want to decompose this. So there's something called the Baker-Campbell-Hausdorff formula, BCH, or Trotter formula, which allows us to do something like this. And what you get is that the exponential of minus I h delta t over h bar is equal to the exponential of minus the kinetic term, delta t over h bar, times the potential term plus an error term that goes as delta t squared. Okay, so this is the error in our approximation. And we're going to ignore this in the limit that delta t goes to 0. So then we consider g of xi ti xi minus 1 ti minus 1 is equal to xi exponential of minus I h t over h delta t over h bar xi minus 1, and this is approximately equal to xi exponential minus I t delta t over h bar xi minus 1 times the exponential of minus I v at xi minus 1 times delta t over h bar. So we're assuming that v is a function of position and t is a function of momentum. And so because v is a function of position, we can just evaluate the action of this exponential on the position eigenstate. Okay, so to evaluate the momentum term, we're going to take a Fourier transform. Here we have some expression of the form e to the minus I t delta t over h bar x prime. We're going to insert a resolution of the identity in terms of momentum. So we're going to take x, well, not forget my integral, first of all. And then we're going to have x e to the minus it delta t over h bar p x prime. And so we're going to take t to be equal to p squared over 2m. Remember, t is an operator, of course. And then what we get is, where did that come from? Oh, yeah. 1 over 2 pi h bar, the integral over dp exponent of minus I p squared delta t over 2m e to the I p x minus x prime over h bar, where we used where is it? Well, I think it's over there, so I'll just rewrite it. xp is equal to 1 over 2 pi h bar times e to the ipx over h bar. So we can evaluate this integral, and we get following expression for each term. We get an expression with the form m over I 2 pi h bar delta t, all square rooted,
term 2 pi h in this step where you introduced the identity?
The identity? No, I don't think so.
Because it seems to be a factor of 2 pi h.
Am I missing?
Or is it either you need a square or need one cancel out or something?
Oh, sorry, this is square rooted. There's mine.
Okay.
Okay, good. In fact, this is square rooted too. Okay, thank you.
I think that
two separate expression factors.
Oh, you're right. This is not square rooted. Okay, good. Thank you. All right, so the upshot of this is that we get, we're going to, take the limit n goes to infinity such that delta t goes to 0, and we're going to ignore error terms. And then we get the full propagator g x t x naught t naught is equal to the limit as n goes to infinity. Just remember my integrals. dx1 to dxn of this prefactor m 2 pi I h bar delta t to the n plus 1 over 2 times the exponential. So what we're doing is we're taking a product of exponentials and making it an exponential of a sum. So then in the limit, we can replace I h bar times the sum over j equals 0 to n delta t m over 2 xj plus 1 minus xj over delta t squared with I over h bar integral from t0 to t. So we're interpreting this as a Riemannian sum is the trick. dx by d tau squared minus v of x dt. We achieve this by interpreting the sum as a Riemannian integral. Along the particle path. I'm sorry? Well, that's just where you think of the You draw the histogram under the curve. You interpret the integral as the sum of the areas of the...
Oh, it's just some areas.
Yeah. Yeah.
You're missing some factors in the bx when you take the limit on going to infinity, exponential, so big thing. And you're missing the factors of you that are compared.
In here?
Yeah. I mean, there's no factors multiply and b, correct?
Like a delta t or something?
Yeah, and that's a t over h bar on minus side.
Maybe you just need a delta t over h bar.
Yeah, there should be
Well, no, I think the problem is we took a product. We took a product of n terms, and n times delta t became 1 because we took the limit.
No, but you cannot sum, I mean, you cannot sum the b's as if they were the same thing.
there should be a delta t before in
I mean,
that x
after that line, everything is okay. But
multiplying this out.
So you think that here this is just collecting terms, actually. We haven't done anything.
It's collecting infinitely many finite terms in the limit, which is a problem.
Yeah, I see that. That's weird.
It's just one.
Yeah, I mean, it should come from in there the t delta t over h bar.
Right, there's missing a delta t. Yeah, I agree. Okay, so there should be a delta t here.
Yeah,
Sorry, what else is it? I h bar? In the I in the numerator? Okay, that is actually a typo also in my notes, so let me just... Can I borrow your pen a second? Thanks. All right, good. So now the key point is to recognize the classical Lagrangian. L of x dot for a particle in a potential is m of x dot squared, 1/2 mx dot squared minus v of x, which is exactly what we have here. And now if we integrate L along a path, we get the classical action. The classical action S, let's use this notation, S associated with the path is equal to the integral along the path of the Lagrangian function. So then we have a very compact form for our propagator. So we have this kind of very, very simple symbolic form, which is the g of xt x naught t naught. Slightly bigger, sure. There's a lot of subscripts here. So this corresponds to a functional integral over all paths connecting the starting point to the final point.
So what happened to the multiple prefactor up front?
Sorry, you guys can't see this. Let me write it somewhere else. Is there a question?
What happened to the prefactor up front? There's normalization or something? Into the n of n plus 1 2. This thing in the brackets?
Yeah, I guess that it gets absorbed into the measure. Yeah, I mean, so there are some very subtle kind of convergence issues for this object that I've never investigated. So I can't comment on, but I do know that there are concerns. Yes?
So I have two questions that are really the same question. So first of all, you're assuming that your potential only has finitely many discontinuities that are each finite jumps, since otherwise you could partition your sum in such a way that you could just miss the discontinuity altogether. So you don't want that V to be huge. Well, yes. And what you're assuming is well behaved. And my second is that how do we know that the prefactor to the exponential is going to be the same no matter how I slice my time?
This prefactor?
Yeah, so I could choose to slice my time in a not equal manner. So the way you've done it, you've split your U's into a bunch of products where the time step between each of the things is equal. But I could choose a different partitioning if I want. How do I know that that thing is the same?
By not choosing a different partitioning.
Yeah, I don't.
I think this
I don't
is
know.
rigorously how you do it.
You just only choose the same finite time intervals. Yeah, I believe that sounds reasonable to me. I haven't seen anyone worry about that before, so I'm not familiar with it. What was I going to say? Right. So, right, this is a functional integral. Over all paths connecting xt to x naught t naught. So notice that the paths can be quite irregular. So this means, basically large jumps. Large jumps are allowed in one time step. Because we treated the x's at successive time steps as independent random variables. Xj and xj minus 1 as independent random variables. So, and the second point is that there are difficulties in making this expression rigorous. So in practice, the integral is evaluated using the discrete model. So the picture you get is something like this. You have time and position. You start out at some point x naught and t naught. We have a whole bunch of small steps of size delta t. And then you have several possible paths. Let's call this x. And then you can have, some other path like that. And then we sum over all possibilities. And so I didn't present it, but there's an analog of a discrete Markov process. There's a classical analog as a And so one thing I forgot to mention is what you see from this expression is that each kind of, classical path, one of these, we'll call it classical, but each definite path, I should say, in this expression has a weighting factor which is given by a phase. And the phase is given by the classical action associated with that path. So paths that are near to each other would have similar actions, and paths that are far apart can have very different actions. And this is closely connected to the fact that the Lagrange's principle, where the path of least action, the path that minimizes the action, is the actual path that a classical system would take. And the picture we get from this is that the quantum system is exploring all paths, and we get a phase factor associated with each path, which gives rise to interference phenomena. So here, this is a generalization of the classical picture, which gives us exactly the quantum mechanical solution, where we weight each path by a phase, and that phase is given by the classical action of that path. So I think that's the key insight of this model. So let me just write that down. We have essentially a sum, loosely speaking, over paths weighted by a phase given by the classical action of that path. Yes.
Something to
Mm-hmm.
To what extent this is a formulation of the quantum mechanics? I mean, I can also formulate path integrals for spin systems and stuff that don't have continuous degrees of freedom like position.
Yeah, I don't know the state of the art in doing a path integral formulation for finite dimensional systems. I know that I was hoping that Rob Speckens would volunteer to give this lecture because he's actually working on right now a generalization of path integrals to finite dimensional systems and trying to understand kind of what's the right classical analog of that and how do we construct that model. So I don't think he's published anything on it, but I know that last year one of his Psi students did a project on exactly that. So I'd encourage you to talk to him. Okay, we started a bit late, so I'd like to just introduce the next topic, which is, we've looked a lot at the discrete time picture, this as being a notable exception, although really in practice this boils down to a discrete time problem. If you want to actually evaluate this path integral, I think one of the few cases where you can evaluate it analytically is the harmonic oscillator. And for every other problem, you resort to evaluating the finite step model. But so we focused a lot on discrete time quantum mechanics, and I wanted to tell you a little bit about continuous time quantum mechanics, and in particular, the problem of describing these generalized possibilities for open systems when you have continuous time. So continuous time open system dynamics. So a simple model for this which is not the most general thing that can happen, is based on what are called quantum dynamical semigroups. Which is a one parameter family. So all that means is you have a set that's indexed by a continuous parameter of bounded linear maps So our family of maps is indexed by t. T is a positive real number. And we require them to satisfy three conditions. So the first condition is that lambda t is a completely positive trace-preserving map for every t. The second condition is that for every bounded operator on the Hilbert space, and density operator H, density operator on H we have that the inner product trace of lambda t acting on rho against our observable h, our observable a, is a continuous function of time. And the third condition is this semigroup property that lambda t composed with lambda s is equal to the lambda you get when you just add t and s. For every s and t that are positive reals. And finally, we assume that lambda 0 is the identity superoperator. So we call this a semigroup instead of a group because we don't have inverse elements. So this is not a reversible picture. This is a model of irreversible dynamics. So this is a model of irreversible dynamics, which is what you expect if your system is interacting with some hot bath and information is flowing into that bath. All right, so I'm going to actually erase here because so the point is this. We have some system, and it's evolving, and it's say, coupled to some reservoir, which is our quantum environment. And we notice that the purity of the system is changing, so we don't have closed system evolution. And so we want to model its dynamics with this picture. So the theory of semigroups guarantees that if we have a set of completely positive maps satisfying these assumptions, then we can actually represent each element, lambda t, as the exponential of another operator L. So notice that there's no imaginary. So here L is a superoperator, and it's just a real, well, it's not real, but there's no I here is what I mean, where the action, if you have some rho of t that's obtained via lambda acting on rho at time 0. Remember, lambda is a CP-TP map. It's a superoperator. Then we have the differential form d rho of t by dt is equal to L acting on rho of t. So there exists an L such that here, I'll put 2 hats on the L. I guess I should be consistent about this, but now that I've started, I already regret it. It's a lot of hats to throw around. So basically, Lindblad showed that the generator L can be expressed in a nice form. L acting on rho is equal to a piece that gives the pure unitary evolution plus another piece called the dissipator, where the dissipator D admits a nice decomposition, a decomposition of the form D acting on rho is equal to a half times the sum over L equals 0 to D squared minus 1. D is our Hilbert space dimension. A coefficient gamma, and an expression of the form AL rho. So this is very similar to our Krauss operator decomposition, except these are operators acting as a generator. So they're inside of an exponential. Where D is the Hilbert space dimension. This model extends to infinite dimensions under certain conditions. So the gamma L are just coefficients. In fact, the gamma L's have certain properties which I didn't write down. I think the gamma L's are real, and I remember working this out last year and forgot to write it down. But so maybe I won't say anything further. But the gamma L are just, well, the gamma L's and the AL's are basically just the set of gamma L's and AL's are essentially the specific details of what the open system evolution is. Yeah, sorry, the gamma L's are real. So let me just say that. So the gamma L's are real. And the AL's are linear operators on the Hilbert space. So this model, this Lindblad picture, has been a very successful model of open system dynamics. So the first kind of experimental platforms in which we were able to do controlled observations of quantum systems in the open system setting were nuclear magnetic resonance and atomic optics. And in both of those cases, I mean, the atomic system is coupled to an electromagnetic field, which is responsible for spontaneous emission and things like that. And the NMR nuclear spins are coupled to some thermal bath. And so these are both open systems that show spontaneous rates of decay. And that can be modeled very successfully with this Lindblad picture. So for about 40 years, this was kind of the paradigm of open system dynamics. And then there's this interesting problem, which is how do you derive this model from a microscopic picture? So in other words, I have my two-level system, and I can phenomenologically, this is a phenomenological model for its open system dynamics. How do we derive this phenomenological model from an exact treatment of unitary evolution of the system and environment that are interacting in some way? So this is similar to the Krauss operators we saw. That's a phenomenological model for discrete time dynamics. And we showed that every Krauss operator decomposition that meant that the map was a CP map admitted some purification via the Stein spring dilation. We could think of it as a unitary that coupled the system with the ancilla, and then we traced out the ancilla. So the question is, can we do the same thing for this continuous time model? And the answer is yes, but it's a lot messier. So there's a series of, the typical way you do this is you actually start from the microscopic model and then derive under some reasonable assumptions what this, derive this phenomenological model. So so an important problem is deriving the Lindblad model, which is a phenomenological model, which basically means that it's an ad hoc model that happens to work. So it's a model built up from observing the phenomena and finding a mathematical description that's adequate for describing that phenomena. So from an exact treatment from an exact description of unitary evolution, of a quantum system coupled to a quantum environment. Yeah.
This is a Markovian approximation to an open system, right?
This is a Markovian approximation.
And that's because you have this semi-group structure.
Yes.
Okay. And when you say that the problem is deriving the Lindblad model, are you saying that without making any approximation of this?
So we found the Lindblad model by just positing that we have this family of maps, and it gave us this picture. But now we want to say, well, let's look at the full unitary description on a bigger Hilbert space and derive this model. And so you can do it, and you have to make a series of approximations. One is called the Born-Markov approximation, other approximation. So we mainly wanted to introduce this because we have one lecture left tomorrow. There are some topics in quantum information we can look at, kind of like selected examples from quantum information. I could do that either the full time or part of the time. Another thing I could do is I could discuss the approximations involved in deriving this Lindblad picture. I probably wouldn't want to spend more than half the lecture, but I just want to know how interesting that was to you guys. Should I spend all of tomorrow's lecture on examples from quantum information, or how many of you would be interested in seeing, instead of the examples from quantum information, some discussion of the approximations involved in getting this Lindblad model? Just by show of hands. Open system model, just a few of you. So the vast majority want to see topics in quantum information? Okay, fair enough.
So one thing with respect to this, we're choosing the lambda is a CPTP map, and this whole like paradigm, whatever, because it's the most general transformation I can make to a density matrix, right, or a state. But I know that there is some other models which are non-Markovian,
Mm-hmm.
which there are more like stochastic models for the description and open quantum systems.
Mm-hmm.
So doesn't that imply that what we did in the whole course, which is this notion of a general transformation, is only valid under this assumption of having Markovian?
Yeah, that's exactly right. If you just say, I have some continuous time evolution over some time period, and then I want to pick some window of time within that time period, and I'm dividing my system into a system and an environment, can I describe the dynamics in that window as a CPTP map? The answer is no, you cannot. So exactly, remember I told you the caveat for our axiom about CP maps was that, well, there's no entanglement or there's no correlation between the system state and the environment state. If you have some continuously evolving system and environment, At any instant in time, there will be correlations between the system and the environment. So if you just want to pull out some discrete time window and say, I want to describe that transformation as a CP map, that will not be valid. So what you have to do is make a series of approximations that ensure the validity of that. And so this is generally what the Born-Markov approximation does. Since I won't cover it tomorrow, loosely speaking, the idea is that you have so you have a weak interaction, and the environment has some very fast dynamics. The environment is big and hot is basically the idea. So you have your system, and it's coupled to your environment, and it evolved for some time. There's going to be some imprint of whatever's going on in the system will be left imprint. There'll be some correlation here between the local part of the environment and the system. But if you describe, if the time scales on which you're describing the evolution are such that you allow kind of in between the time steps, you allow the environment to have some very fast dynamics, much faster than the system-environment coupling, then the local imprint, the correlations, get swapped out to some other part of the environment, and the part of the environment that was over here that was uncorrelated gets swapped in. So this is the fast environment dynamics.
So basically, your correlation function as function of time decays.
Yeah, so you want your correlations to decay faster than the time scale in which you're observing the system. And that's why this model is it works very well to describe atomic optics and NMR, because those conditions are met. And so it turns out if you look at like spontaneous emission on a time scale of like 10 to the minus 15 seconds, you can see deviations from the Markovian assumption. I don't know if this has ever been done experimentally, but I think it's theoretically expected. But then in more generic systems like superconducting circuits and so on, this condition may not be met. And in fact, this is an important problem for designing quantum devices. We'd like to stay in a Markovian regime so that we can both mathematically and experimentally understand what's happening with the system, but that condition isn't always met. So you essentially have a series, the Born-Markov approximation is needed to guarantee the Lindblad form. It's actually a series of approximations are needed to guarantee the validity of the Lindblad picture. And a common way that people talk about this is to say that the local environment can have no memory of where the system was previously. And one way to do that is to be swapping out the environment very fast. Okay, good. Well, we'll see you tomorrow.